Hello, everyone. My name is Megan Heaviside, and this is our project. My team consists of Brian, Vikram, and Stephen, who will be introducing themselves shortly as well. So the problem statement is earthquakes are a common problem in California. We're designing an automated way to support victims by reducing their waiting time to receive help and aiding first responders. California is frequently affected by seismic activity. Southern California alone experiences over 10,000 a year. Earthquakes occur with no warnings and can rapidly cause a lot of damage to the affected zone in a very short amount of time. This design aspires to aid in the recovery efforts of victims and provide support to emergency responders. Currently, earthquake response in California is handled by the federal and state emergency response teams, as well as other organizations. With the use of these robots, the agencies can more efficiently manage their response, as well as help more of those in need. The target users for our designs would be directly the police department, firefighters, US Army, and the federal and state disaster response teams. Indirectly, users would also be the health and public services or policymakers who could be involved in the implementation of these robots.
Hello, my name is Vikram Rubicam. The design requirements for our swarm are as follows. The swarm should be able to locate victims within a 50-mile radius. It should be able to provide first aid kits to victims, move 100 pounds of debris, and transport victims or notify emergency workers of victims' locations if needed. The design also must detect when an earthquake occurs and must reach a range of 50 miles within the affected locations before rescue teams arrive.
Hi, my name is Brian McAllen, and this is the Swarm collection of robots. The first robot is Obstacle Remove Robot, done by Brian McAllen, which clears rubble and debris to reach and assist victims. Next, we have the First Aid Kit Delivery Drone, which is going to be done by Megan Heavenside, which delivers first aid kit to victims in need. Next, we have the Victim Locator, which is going to be done by Bikram Arumahab, which identifies and relays location of victims. And lastly, we have the Medical Evacuator, which is going to be done by Stephen Hall, which carry injured people and delivers to first responder teams. Here's the design of the robot. There are three different views, front, side, and top. The measurements of the robot are 5 times 5 times 7.5 feet, which is a large scale designed to complete the task of removing debris up to 100 pounds. The bottom part of the robot includes two DC motors that are going to be attached to two central shafts, and those shafts to the rotors, which are going to cause the motion on the wheels. The hands are going to be operated by one DC motor, which is going to move the gears, and those gears are going to move the mechanism inside of the arms that we are going to cause the expansion of the arms up to 2 feet. The top part of the robot includes DC motor, which moves the arms, battery pack, ultrasonic distance sensor, temperature sensor, and two tilt sensors. One of the changes that occurred to this design is that one tilt sensor was added. Here, the electrical design of the robot includes one Arduino, three DC motors, two batteries, one distance sensor, one temperature sensor, two tilt sensors, and two L2930 chips. The two batteries were connected in series to provide enough power and efficiency for the motors. One of the chips controls the motion of the robot. The other chip controls the motion of the arms, which causes the expansion and retraction. The tilt sensors detects any changes in inclination on the ground. The temperature sensor detects any change in temperature in front of the robot, and the distance sensor detects any obstacle in front of the robot. Here is a flow chart of the robot. When there is no inclination registered, the central hub is going to be signaled that activity is normal. Whenever there is a change, the central hub is going to be alerted, and robot 3 is going to be alerted. Then the robot is going to start to move in. Whenever there's an obstacle less than 10 feet, it's going to start moving forward and expand the arms. Whenever it sees a change in temperature in front of the robot, it's going to alert robot number 2, and it's going to reverse. Now, when it receives a signal from the hub, it's going to become an obstacle remove, avoid obstacles until he reaches the location, and then it's going to start pushing out the obstacles. Here's a snapshot of the Arduino code, which includes most of the sensor inputs. You can see the input, distance sensors, actuator input, tilt sensors, temperature sensors, and here's some of the other commands that were added to the design. Now we're going to proceed with the simulation. Activity normal is going to be displayed when there is no change in an inclination. Whenever there is an inclination, the central hub is going to be alert, and robot 3 is going to be alert as well. Whenever the robot sees an obstacle less than 10 feet, it's going to start moving forward. And arms is going to start expanding, and at some point it's going to start retracting. Whenever it sees a change in temperature, it's going to start reverse and then stop. Whenever there's an input from the central hub, the robot is going to start proceed to move forward until he sees an obstacle less than 20 feet. Whenever he sees an obstacle than 20 feet, it's just going to stop. Then it's going to reverse and turn right. Then it's going to proceed to move forward until he reaches his goal. Now we're going to proceed with the next design.
So this is my design. This is the first aid kit delivery drone, and this is the mechanical design. This drone's task is to deliver first aid kits to earthquake victims. It would receive the victim's location from the central hub. You can see the different views of the drone here. There are 3 distance sensors in blue. There's one in the front, right, and left. There's 4 DC motor powered rotors. If you see on the bottom, there's little black dots that would represent how the first aid kits would be secured into the drone. The drone can hold 4 first aid kits at a time. This is my circuit design for the first aid kit delivery drone. You can see I made use of an Arduino. There's 4 DC motors, 3 distance sensors, 1 at the front, right, and left. The motors are powered by 9-volt batteries. I did use 2 L293D chips as well to connect the motors. Each motor is connected to a digital pin and an analog pin to be able to change the power to each motor as necessary. So this is the flowchart for my drone. The drone would start and it would make sure it has first aid kits in supply. So if it's out of first aid kits, it would return to the first aid kit station and load 4 more kits. If it's full of first aid kits, it would receive the victim location directions from the central hub. The drone would hover and it would receive the various central hub inputs that give the directions. So for example, A would ascend, D would descend, R goes right, and so on. There's also the ability to detect obstacles with the distance sensors. If it did detect an obstacle, it would hover and await updated instructions from the central hub. And then once it did reach the victim location, it would drop off a first aid kit and continue to do that until there's no more victims that need first aid kits. This is my Arduino code. So there are various functions for ascending, descending, going forward, going right, etc. And there's also the central hub inputs that I used characters such as D for descend, F for going forward, and so on. There's also the distance scan and obstacle scans. Distance scan is obviously using the distance sensors to measure the distance in inches. And then obstacle scan would take the distance from the front, right, and left. And if it's less than 12 inches, it would let us know that there's an obstacle detected in the front, right, or left. And then at that time, we would update the flight instructions accordingly. So now I will be starting my demonstration, which will show the circuit in action. So I'll go ahead and start the simulation. And you can see that the drone starts by hovering. You can see that right motor 1 and left motor 2 are going counterclockwise, and the right and left motor 1 are going clockwise. So as it's hovering, it starts by saying it's receiving victim location from central hub. So I have the various central hub inputs that would be given to this drone. For example, you can go right with the R, and you can see the 2 motors, right motor 2 and left motor 1, have more power, and that allows it to turn right. And then the opposite would be the L. You can see now these 2 motors have more power, and that would allow it to go left. Another example would be the A for ascending, and that gives more power to all of the motors, and that would lift the drone. Obviously, D would do the opposite and would lower the power to all of the 4 motors, and the drone would descend. And finally, to demonstrate the obstacle detection, you can see the front distance sensor here. There would be an obstacle about 1.6 inches away, and you can see here it says obstacle detected in front, and we would update the flight instructions.
My design for the victim locator drone, shown from multiple viewpoints here, is approximately a foot in length and width. and 3 inches in height. Its small size mitigates costs without sacrificing effectiveness. The design consists of a main body, 4 small beams that protrude from the body, and a propeller powered by a DC motor on the end of each beam. There's an ultrasonic distance sensor on the front, top, and underside of the drone for detecting obstacles. The drone also has on the underside a PIR sensor for detecting the motion of victims. The PIR sensor can be rotated in an arc of 180 degrees from left to right by the connected servo motor to expand the sensor's field of view. The propellers allow the drone to move in any direction, and while the drone is in motion, the distance sensors detect obstacles and the servo motor and PIR sensor locate victims. The mechanical design remains unchanged since the proposal. The circuit from our drone, as shown, consists of an Arduino board, 2 breadboards, 2 9-volt batteries, 4 DC motors, 3 ultrasonic distance sensors, 2 L293D chips, a PIR sensor, and a servo motor. The Arduino board controls all the sensors and actuators. The L293D chips help connect the motors, and the batteries power the motors. The motors utilize 1 analog and 1 digital pin each on the Arduino, so that the power supplied to each individual propeller can be controlled. The motors and servo motor move according to input from the central hub, and the distance sensors and PIR sensor relay information about obstacles and victims to the central hub. Input from the distance sensors and PIR sensor can also affect the movement of the motors if an obstacle or victim is detected. The electrical design also remains unchanged since the proposal. Here is the flow chart for my drone. The drone first receives the location of the affected area from the central hub, and then flight instructions represented by the letters shown. The first 6 instructions will change the power supplied to the drone's motors so it moves in the desired way. The drone can also receive the S instruction, in which case it will swivel the servo motor to move the PIR sensor. Only ascending, descending, or moving forward can bring this drone closer to an obstacle, so the drone only receives input from the distance sensors after one of these actions. If it does detect an obstacle, it hovers in place and informs the hub so that the hub can guide it. Eventually, regardless of which letter instruction is given, the flowchart leads to victim detection, except when an obstacle has been detected previously. If the drone detects the motion of a victim, it will also hover in place and inform the central hub of the location of the victim, so that other robots and emergency workers can reach the victim. Lastly, if the victim locator drone has flown over the whole affected area and finds no more victims, its job will end. The overall logic also remains unchanged since the proposal. Here are a few snapshots of the Arduino code for my drone. As seen, the code includes the setup function, the loop function, functions controlling motor power, and functions for identifying obstacles and victims. Now I will begin the demonstration. I'll first start the simulation, and the drone will take a few seconds to take off and prepare for further instructions. So we can see that right now all the motors are spinning at about the same speed, with 2 spinning clockwise and 2 spinning counterclockwise. Now let's say I tell the drone to turn left, L. In response, 2 of the motors are now spinning at a lower speed, and the other 2 are spinning at a higher speed. So after giving it a little time to turn, I now want it to hover in place, H. This sets the speeds back to their original value. If I then tell it to ascend, A, all the motors will increase their speed. Finally, I want it to go forward, but then detect an obstacle a foot away, which is the distance threshold I have chosen. So I told her to go forward, F. The motor speeds changed accordingly, and then I moved an object a foot away from the front-facing distance sensor. In response, the serial monitor gave an obstacle detector alert, and the drone is now hovering in place to await instructions for guiding it around the obstacle. Now I'll start the second simulation and wait for the drone to prepare. Then I'll invoke the servo motor movement, and when the servo motor finishes moving, the PIR sensor will detect a victim. So the S instruction made the servo motor swivel in a 180-degree arc, and then once the PIR sensor detected a victim's movement, it gave an alert in the serial monitor. The motors would have also changed speed to hover if the drone had not already been hovering.
Hi, my name is Stephen Hall, and here's my design for the medical evacuator robot. Below are 3 different views of this robot, including front, side, and top. The dimensions for this robot are 5 by 2.5 by 2.4 feet. This design is created to load those injured or in dangerous locations and transport them to safety where first responders can tend to their injuries. The robot consists of a main body which features a conveyor-like belt. This belt will run off a DC motor and will be used to load the injured onto it. This robot also has 2 tank-like tracked wheels which will also be powered via 2 DC motors. This robot also has an ultrasonic distance sensor and a PIR sensor, which will be used to detect the victims. The circuit design is as shown. The circuit consists of an Arduino board, 2 breadboards, 2 9-volt batteries, 3 DC motors, a PIR sensor, an ultrasonic distance sensor, and 2 L293D chips. The sensors are all controlled by the Arduino, while the DC motors are powered via the 9-volt batteries, and the L293D chips connect them both together. Here's a flowchart to explain the overall logic of this robot's programming. So at the start, the medical evacuator robot will receive the location of the victim as well as directions to reach the victim. As it begins, it will move along the path, and any obstacles detected via the distance sensor will cause the medical evacuator robot to change its course to avoid these obstacles. Once it reaches the victim, it will detect them via the PIR sensor. Once detected, the medical evacuator robot will load the victim and return to emergency personnel. As it returns, any obstacle detected will cause the medical evacuator robot to change its course until finally it reaches first responders where the victims can be tended for. Here's a snapshot of my code. It contains many different commands that the central hub can direct this robot to do based off any input from its PIR sensor and ultrasonic distance sensors. These instructions tell the robot where to go, such as move left, right, forward, and reverse, as well as when to load the victim and any obstacles that it may see along its path. So let's take a look at our circuit here, and let's test out the code that it will use based off of different conditions. In our code, this will be the code for the forward. So as we see, let's see if it works. See, both sides will be moving. This will allow the robot to move forward, and say we need them to turn right. It would just be adjusted. And let's see. Yep, so this right side doesn't work, only the left side motor, which would cause the robot to turn right.
This is the flow chart displaying the collective behavior of our swarm. First, the obstacle remover must detect earthquake vibrations to activate the swarm. Otherwise, the central hub simply displays a no activity message. Once vibrations are detected, the central hub is alerted, and it tells the victim locator drone to start searching. If a victim is located, the central hub notifies emergency workers, and all other drones are sent to the victim's location. The obstacle remover will remove debris at the site, while the kit delivery drone delivers a first aid kit and medical evacuator loads the victim onto a stretcher. Once the victim is loaded, the central hub will send the evacuator's location to emergency workers. Also, if the delivery drone runs out of kits, the central hub will tell it to pick up more from the station. At the end of all of these actions, the flowchart loops back to the victim locator's detection.
Entry pre-analyzed market ready cost is $16,800. The large dimension of robots 1 and 4 require multiple custom parts to be manufactured in order to assemble these robots. Therefore, they will contribute to the highest monetary cost. The vast amount of available manufacturers and material in the current market for drones makes these robots 2 and 3 relatively inexpensive. Similar products do not exist in the current market. However, prototypes for search and rescue during earthquakes exist. Japan built a set of robots after 8.9 magnitude earthquake struck the Iceland in 2011. These robots will not be able to locate people quick since none of them move in the air. Also, these robots will move slow. The robots presented today can do good tasks efficiently by working collectively. One of the key points of the project are rescue emergency teams' exposure to hazards will be reduced. Response assistance will be more effective. People will be supported in a timely manner. People under debris will be localized quicker.
So in summary, this project taught us countless lessons and tools to help us in our engineering career, such as the engineering design process, how to best select designs using data such as the AHP and decision matrix, as well as how to use Tinkercad and other CAD softwares, as well as the Arduino programming. This project also taught us how to effectively manage projects, as well as how to create and use a Gantt chart. Throughout this project, our team worked well together. However, time management was an issue that we could have done differently if we had the chance to redo it. Throughout this presentation, we have showcased our robotic swarm, which was developed to act in tandem to accomplish various tasks related to search and rescue from earthquakes. For each of our 4 robots, the mechanical and electrical designs were shown, as well as the Arduino code that was used to control them, and finally, flowcharts explaining the overall logic of these robots. Thank you for watching.